Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Haziq Izani bin Hamizi. I'm the leader. So, my matrix number is CB250161. So, I want to present the group final project, and the title is Trigonometry in Action, Real World Measurement Around Campus. So, the code kursus is BBP 10603, Matematik 1. Okay, now the next page is our team. The first one is Muhammad Haziq Izani bin Hamizi, is me. The matrix number CB250161. And the second one is Adriana Dalina binti Zamri, CB250242. And the third person is Muhammad Raidi Zafran bin Roslan, CB250356. And the last person, Muhammad Nazmizan bin Junaidi, CB250105. So, the next page is our content. So, the first one is introduction, then objective, then activities, then diagram or drawing trigonometry, then discussion and error analysis, then conclusion, recommendation, then bibliography. Okay, so the next is introduction. When dealing with distance and height that are difficult to obtain directly, through this assignment, student will apply fundamental trigonometric concept to estimate real-world measurement of various structures around the campus. By collecting and analyzing data, students will be able to verify the accuracy of their calculation and deepen their understanding of how trigonometry function in practical situations. In addition, these tasks encourage effective teamwork, liberate to carry out measurement activities and present their finding. Overall, the strengths both of mathematical reasoning and collaborative problem-solving skill through hands-on application of trigonometric method. Okay, now we go to objective. The first one is apply trigonometry concept to measure real-world distance and height of campus structure. The second one, interpreted and analyze collected data to verify the accuracy of trigonometry measurement. The last one, collaborate effectively in group to conduct campus based on measurement activities and present finding. So, I will tell you about the first activities that we choose. The first one is flagpole angle of elevation. This activity was conducted near an open area where a flagpole is located. The height of the flagpole was provided, and the horizontal distance from the observer to the base of the flagpole was measured using a measuring tape. The observer height was logically assumed to be 1.60 meter, represent an average eye level height. The objective is to calculate the angle of elevation from the observer to the top of the flagpole. Okay, for this slide, I will explain how to calculate the angle of elevation for the flagpole. On the left side, we have a simple diagram showing the situation. The height of the flagpole is 250 meter and the observer is standing 236 meter away from the base of the pole. The observer eye level is 1.70 meters. To calculate the angle of elevation, we first find the difference between the height of the flagpole and the observer height. So the actual height used in the calculation is 250 meter minus 1.70 meter. So we got 258.3 meter. Then we use the formula shown on the slide. Theta equal arctan hash height minus observer height over d diameter, where height is the height of flagpole, observer height is the height of the observer eye. D is the horizontal distance from the observer to the flagpole. This formula will give us the angle formed between the observer line of sight and the ground. This is what we call the angle of elevation. So, the next activity that we choose is staircase slope angle. This activity was carried out at a staircase around the campus. A measuring tape was used to measure the vertical height rise and the horizontal distance is run of the staircase. The purpose of this activity is to determine the slope angle and compare it with the accessibility requirement, which state that a ramp of staircase should not exceed 12 inches to be recording possibility.
Assalamualaikum, my name is Muhammad Azmizan bin Junaidi, metric number CB250105. So this is a diagram of staircase slope angle. We can see a diagram to determine the angle of inclination of a staircase. The rise value is 170 meters, while the run is 276 meters. To obtain the angle of inclination, we use the formula 0 equals the extent of rise divided by run. Based on this measurement, the angle of inclination can be accurately calculated to assess the safety and suitability of the staircase design. In this slide, I explain the angle of cable support. This activity is done to determine the angle of cable supports connected to a structure. We measure or estimate the vertical height as the opposite side and the length of the cable as the hypotenuse. Using trigonometric ratios, the angle between the cable and the ground surface can be calculated to ensure the stability and safety of the structure. On this slide, we have the diagram of calculating the cable support angle. The opposite side of the triangle, which represents the vertical height, is 275 meters. The cable length, which is the hypotenuse, is 368 meters. To find the angle between the cable and the ground, we use theta equals sin of opposite divided by hypotenuse. By subtracting the values, we can determine the exact angle formed by the support cable. This calculation helps us how to understand the steep or how stable the cable support is when attached to the structure. So, this slide is about height of street light or a shadow method. This activity was conducted in an open area where a street light and sufficient sunlight were available. A broomstick of known height was used as a reference object. The height of broomsticks and the length of its shadow were measured simultaneously with the length of the street light shadow. Since the sun's rays create parallel lines, the angle of elevation is the same for both objects, forming two similar street angles. The purpose of this activity is to calculate the unknown height of the street light by comparing the ratio of the broomstick height and shadow to the street light shadow. This slide shows how we calculate the height of a street light using the shadow method. The shadow method is based on the concept of similar triangles, where the ratio of height to shadows is the same for all objects under the same sunlight. First, we use a broomstick as a reference object. The height of the broomstick's h is 120.22.8 centimeters. Next, we measure the shadow of the street light, which is 1,200 centimeters. Since both of broomstick and the street light receive a sunlight at the same angle, their triangles are similar. The calculation is shown in the slide. So this is a drawing from us. As we can see, on the left is a drawing from flagpole angle elevations, and on the other side is a drawing from staircase slope angle. This is also a drawing that we have drawn. On the left is a drawing of cable support angle, and on the right is a drawing of height of street light or a shadow method. Thank you. So this slide is shown about our discussion. In this project, trigonometric methods were used to determine an angle based on measured distance or height. Theoretically, the calculated angle should closely match the angle measured using a physical measuring instrument, such as a protractor, clinometer, or digital angle meter. However, the result shows a noticeable difference between the calculated angle and the measured angle. This discrepancy can be attributed to several factors, including manual measurement errors, instrument limitations, and environmental conditions during the measurement process. Thank you.
Okay, thanks Mizan. So now that we have looked at the calculation, we need to address the reality of fieldwork. Our calculated result didn't always match perfectly with the expected values, and this brings us to our error analysis. First, we identify systematic error. These are issues inherent to the tools or method we use. First is instrument inaccuracy. We have to consider that our protractor or clinometer isn't a high precision laser tool. Manufacturing tolerance mean the zero mark might not have been perfectly aligned, introducing a constant slight deviation in every reading. The second one is measurement error. Any small mistake in measuring the base distance or height has a ripple effect because we are using trigonometric function like tangent and sine. Even a tiny error in distance can amplify into a much larger error in the final calculated angle. Next, let's take a look at page 18. We face random errors, which are unpredictable and vary from one measurement to the next. Parallax error. This happens depending on where your eye is positioned when reading the scale. If you are looking straight on, the angle might look different. For example, like if here we look at from above, it's not the same like if we look from below. Okay, next is instability. We were holding this instrument by hand. Even a steady hand shakes a little, causing the reading to fluctuate. Environmental factors. Of course, being outdoor means windy or vibration could affect the equipment, leading to the inconsistent of a data. Page 19. Finally, there are human errors. The mistake that we as a human might have made. First is a misalignment. It's actually quite difficult to eyeball the measuring device, so it is perfectly aligned with the target object. A slight tilt throws off the geometry. The second one is grounding. We also had to be careful about when we rounded our numbers. If you round a decimal too early in the calculation process, the final answer drifts further away from the accurate result. Okay, based on these challenges, we have a few recommendations for anyone that is trying to replicate this experiment. The first one is we suggest that you upgrade the tools whenever possible. Use a digital angle meter or laser measure for better precision. And second one is stabilize. Use a spirit level to ensure true horizontal alignment. The third one is repetition. You must remember, repetition is the key. Don't just trust one measurement. Take 3 to 5 reading and average them out to minimize those random error. The fourth one is math hygiene. Avoid rounding your numbers until the very final step to keep the trigonometry accurate. And lastly, body position. Ensure the observer is positioned directly in line with the scale to eliminate that parallax error we mentioned earlier. In conclusion, while there were differences between our calculated angles and the measured angles, these were expected due to the combination of systematic, random, and human error we just discussed earlier. However, despite these small discrepancies, our results are still valid. They successfully demonstrate that trigonometric methods are highly effective for estimating height and distance, provided that measurements are taken with care. Page 22. Here, take a look at our fieldwork in action. You can see us measuring the lampposts, staircase, and pillars around campus. These practical sessions were where we apply the theory we just discussed earlier. 23. That brings us to the end of our presentation. Thank you very much for your attention. And that is all from us. Assalamualaikum.